Yes, thank you for being here on a Saturday afternoon in Austin. I'd like to talk today about HPC in the cloud and scalability in the cloud and some of the use cases that we are seeing from customers deploying on AWS, again, at scale on the cloud, across enterprise applications, across industries, as well as research. I want to talk about scalability in particular. I'll show some examples of customers that are deploying large-scale simulations, for example, on AWS, how they're doing this, some of the automation that they're putting in place. We're going to talk through those use cases fairly quickly and then dive down into some of the capabilities of the cloud, what you get in a virtualized environment, how you use automation to stand up HPC clusters, and how you think about parallelism in a different way and job scheduling in a different way on the cloud. And then finally, we'll give you some pointers to how to get started. We actually have, for attendees here at the conference, we have some credits. So if you want to get started with AWS at zero cost, we can show you how to run some HPC simulations on the cloud and provide you the credits to do that. So before you leave, be sure to get the cards that we're giving out that will have a pointer to those credits. I should also mention in the back of the room, Linda Hedges, Dougal Ballantyne from our HPC Solutions Architecture team. If you need questions answered after this session and go deep, those are the folks to talk to. So we're going to move fairly quickly in the interest of time. But why are HPC users going to the cloud now? It is primarily about getting scalability. Not so much to reduce costs, although it can be dramatically cheaper to run HPC in the cloud, but more to get time to results much faster, right? To get your scale your simulations much higher, run many more parallel jobs and get things done quicker without the need for a job scheduler. And I'll talk about that concept in a few moments. It's very powerful when you can scale to tens of thousands of cores on demand, very cheap. But perhaps more importantly, you can think about putting other applications in the same place. Big data applications. Data, of course, has gravity. So if you can keep the data and the compute in one place, it's far more effective and it's far more secure as well. Just want to mention that global scalability is critical. We have customers now that are operating very large compute grids on AWS that in many cases span the globe. You don't have to, of course. You can keep all your compute in one of these regions, but we continue to expand. We have regions now across the world, as you can see. We've recently announced that we will have regions soon in India, in Korea, in London. So we continue to advance and add these new regions over time. When we talk to simulation customers, again, whether they're commercial customers in industry doing large-scale engineering projects, or they're life sciences customers, right, or they are customers in research, we hear, of course, that they're looking for scalability, the ability to scale up very fast and scale back down when they no longer need that cluster. But they also talk to us about the need for secure global collaboration. I touched on this a moment ago. The idea that a researcher in Europe, for example, can collaborate with researchers in the US and in Asia on that same data in a very secure way. Which leads to the discussion of data governance. For many of the customers that we work with, that data sovereignty and data provenance is very important to them. So doing this in a very secure environment, in a very monitored and managed way, is very useful. And we have customers now publicly stating that, including NASA, for example, recently stating that what they can do on the cloud is more secure than what they could do on-premise. When we look at the use cases out there on the cloud today, we talk to our customers, we see a lot of legacy HPC applications now moving to the cloud. Good examples here in the simulation space, things like antenna simulations, things like life sciences simulations, genomics and proteomics. There's actually a lot of CFD now being run in the cloud, which is not something you would traditionally think of as a cloud-based application. But lots of innovative companies now doing CFD as a service, or individuals that are running CFD and other applications like that at scale to do very large parameter studies. Finite element analysis, molecular modeling, oil and gas reservoir simulations, weather simulations, all of these now are running quite high scale on the cloud. When we talk about traditional methods of deploying HPC, if you're an HPC user today, you understand the challenge of capacity, right? a small manufacturer, a large research organization, whoever you are, if you're deploying on-premise or owned and co-located perhaps HPC resources, you face this capacity challenge. In an ideal world such as this, you would always have enough resources available to run every job you need to run when you need to run it. Well, this is an ideal situation, so you continue to add new servers, new racks, you keep up with the latest innovations, and you always stay ahead of those capacity needs. Of course, that never happens. What happens is this. You instead have some compromise between your peak needs and those valleys because you want to operate at a high utilization. And the result, of course, is that jobs get delayed, you use job queuing software, or perhaps you delay entire projects until the point at which you do have enough servers. This is the reality today. So our take on this is that HPC job queues in particular are evil. You should get away from them. There's always a need, of course, for job scheduling and workflow management tools, whether you're running in the cloud or running on-prem. But the basic concept of managing to a fixed piece of infrastructure that has only so many cores, with so many jobs being thrown at it, really becomes a bit of an archaic idea when you move to the cloud, because you can scale up as needed, almost a ridiculous amount as needed when you need to run those jobs quickly. In a traditional HPC environment, whether it's an enterprise environment or a research environment, you've got this inherent conflict of goals, right? You've got a central IT team that's managing that cluster and wants to run at a high utilization for cost optimization, but then you have the actual consumers of that resource that are throwing jobs at the queue and expecting fast results. They don't care about utilization. All they care about is getting the job done fast. It's an inherent conflict of goals, right? Another way to look at it is if you use job queuing software, if you use cluster management tools, you probably have some graphs around, and graphs that might look like this. The central IT team that manages that HPC resource may be very proud of a graph that looks like this because it shows very high utilization, right? So you can report to the people that are writing the checks that you're actually getting great utilization of that resource. In this case, over 80%, which is a almost ridiculously high utilization in many organizations, but in some well-managed organizations, this is what you do see. But actually, the flip side of this is what does it look like to the end users? If you look at how many jobs are in the queue over a given time frame, for example, this may be a month, it may be a year. While the central IT team may be looking at this in terms of that utilization graph, the end users are impacted by this, the jobs in the queue, the time waiting in the queue. It's a serious problem in HPC environments. So again, get rid of that constraint. Scale up the clusters as needed. Use cloud resources to scale very large numbers of jobs in parallel, to spin up different kinds of clusters that are application optimized. For example, if you have certain codes that require high memory versus codes that require high CPU density, spin up different types of cores, different types of servers for those in the cloud on demand. And use automation, right? You can use automation in the cloud now using something called a virtual private cloud that I'll talk about in a moment, and using automation tools that we can provide to do a lot of the same kind of job management and workflow management methods that you used previously on premise, but use those in a scalable cloud environment, automatically scaling the clusters up and down as needed. And using traditional job management and job queuing software, traditional schedulers, just as you did before, but again, in a more scalable manner. I'm going to flip and talk about some examples. We have so many examples now, public cases of customers that are running at scale HPC. I'd like to focus in particular on manufacturing customers. We talk to a lot of manufacturing customers that have a need for scale and have new simulation requirements that perhaps they didn't have even quite recently. Good example of this, HGST, the disk drive manufacturer. They've spoken publicly a number of times about their path to the cloud, their migration to the cloud over time, which was triggered really by the divestiture of the disk drive division of Hitachi, Hitachi Global Storage Technologies, out of Hitachi and the sale to Western Digital. That happened a couple of years ago. As a result of that divestiture, they lost access to a lot of Hitachi's central IT, HPC clusters and the like. They had to rethink what they were doing as an organization in support of their engineering needs. At the same time, their simulation requirements were going through the roof. HGST develops very advanced disk drives. Perhaps you use them in your own installations. These disk drives today are helium-filled, highly dense. To develop these disk drives requires tons of simulations, magnetics simulations, thermal simulations, CFD simulations. So they made a decision, the CIO of the organization, Steve Philpott, made a decision that they would go cloud first, right? So they would really run everything they could in the cloud, including these large simulations. And working with partners like Cycle Computing, an AWS partner, they are able now to deploy sometimes 70, 80,000 cores at peak devoted to a single set of simulations. Again, parameter sweeps for these large magnetics simulations that they need for disk drive design to investigate perhaps millions of different disk drive head designs, right? That's a very typical use case that we're seeing in manufacturing, the idea that you want to explore the design space much, much wider and do this using cloud. Trek Bikes recently spoke at one of our events, very similar use case. In this case, it was a CFD use case. They're using Star CCM. They're using software from Rescale, in this case, another AWS partner, to scale this in the cloud and do those design explorations, to do those very wide parameter studies for bicycle design. Lots and lots of examples like that out there today. What enables this for these customers, whether they're looking for security, whether they're looking for job management capabilities, automation capabilities, is the virtual private cloud that's provided on Amazon Web Services. With a virtual private cloud, a VPC, you can really stand up a virtual data center in the cloud. All of the security and compliance requirements that you need, the ability to set up your subnets, set up your identity and access controls, monitor the system, all of those things that you would expect as, let's say, an enterprise or academic and research installation for your on-premise clusters, and far more as well. Many of our customers who are in this enterprise domain and manufacturing and other domains, they want to have a hybrid approach where they still have some on-premise infrastructure that's connected into this virtual private cloud over VPN or via a service we call Direct Connect that allows you to have a private connection into AWS from your on-premise environment and never traverse the public internet. Very common use case now for enterprises that are moving to the cloud, this hybrid approach. Another benefit of the VPC is you can set up the network topology so that it really mirrors what you've got on-premise. You can extend your subnets from the on-premise world out into the cloud. You can extend license servers across that border. Lots of capabilities. And you can lock down sections of that VPC for specific users, for specific applications, under the control of the security and compliance teams of your organization. Again, tons of examples of this. In the life sciences space, DNAnexus has been a great story for us, scaling up quite dramatically over time in support of life sciences customers. Recently, they've published with Baylor, their CHARGE project, doing genomics analysis for thousands of different participants, tremendous numbers of runs, scaling up using Spot instances that I'll talk about in a few moments to run, again, very high-scale workloads on AWS. In this case, like HGST I mentioned earlier, they're using these Spot instances to scale up to tens of thousands of cores in support of this analysis and to bring the time to results down quite dramatically. Another great example, just public quite recently, was Walt Disney has talked about how they're doing rendering in the cloud. POC projects at this point, but they have talked about production rendering for major projects in the future. You can see their full presentation on SlideShare if you're interested. It's a very good presentation because it goes quite deep into their use of Spot instances and their use of VPC to create this hybrid environment of on-premise rendering with the cloud. And like the other use cases, they're spinning up tens of thousands of cores on AWS at a very low cost to enable this. If we dig a little bit deeper into that use case, rendering use case, or if we're talking about simulations as well using a VPC, the pattern that we're seeing is becoming quite common and templated even. In the VPC, as you expect, you might have servers that are being stood up on demand, scaling up perhaps automatically in response to need, connected into the on-premise resource using either our Direct Connect or a VPN. If you want to maintain everything in the cloud, not only the compute and the storage, but also the login nodes and just push pixels back and forth, that can be enabled through the use of GPUs in the cloud to create a graphics workstation in the cloud. Lots of customers now doing that quite successfully for engineering simulations, for energy sector types of use cases as well. Digging a little bit deeper into this, on the lowest boxes, the two below, you can see some storage layers. And this could be done using, let's say, Intel Lustre to set up a shared file system on the cloud, or using third-party partners of various sorts to create storage caching layers within that VPC. You see on the left the use of Amazon S3. That's an object storage. That's a highly durable, 11 nines of durability, a highly redundant storage system, and that really is, for most of our customers, the source of truth. That is where their long-term data storage would be, in S3. And then as needed, they can move that data from S3 into their VPC to do their runs, to do their processing, perhaps using something like Intel Lustre during the course of that computation, and moving it back into S3 when they're done, accessing that data perhaps from other applications or remotely. There's a number of ISVs now that have embraced the use of cloud for simulations. One of them that's here today, Altair, of course. Altair has HyperWorks Unlimited. This is an appliance approach, somewhat like software as a service, where you as a customer can go to Altair, sign up with your accounts, and then they can deploy the suite of Altair solvers and the remote desktop environment on the cloud using AWS. And they've been showing this at conferences. It's actually quite impressive how it works. Lots of solvers in there, job management tools and the like. ANSYS has also done something similar. They call this their ANSYS Enterprise Cloud. This is a little bit different from the Altair approach. It's not a software as a service. It's more of a portal. It's a way for you as a customer to deploy ANSYS software into your own AWS virtual private cloud. Slightly different approach, but the end result is the same. You're able to run your simulations, store the data, and visualize the results graphically all in the cloud. Well, let's switch now and talk about capabilities. We've talked about use cases. We've talked about what customers are doing. Let's talk a little more about how they're doing it and how they're getting performance that's needed for these solvers, for these applications. We're very much in line with Intel in this. We offer our customers environments in which they get access, very low-level access, to the capabilities of Intel processors. This is a virtualized environment. But in the case of our larger instance types that are typically used in HPC and solvers, you get extremely high performance, very low overhead in terms of virtualization overhead. You get access to capabilities of, for example, Haswell and the AVX2 instruction set, the ability to control power states and so forth, C states and P states in these instance types that we offer. By way of a little vocabulary here, when I say instance type, we're really talking about a virtual server in the cloud that has a particular set of characteristics. It may be a certain generation of Intel processor with a certain amount of RAM, certain storage architecture. That is an instance type on AWS. And we have many, many instance types today. Our most recent instance types, the ones of most interest to the HPC community, are our C3s, C4s, and now our M4s. And these, as I said, use the latest generation Intel processors. They're not oversubscribed. You're in a virtualized environment, but the overhead is quite low. And you do get access to these advanced features if you're using Intel compilers, for example, and taking advantage of AVX2. These are increasingly dense. We're offering up to 40 vCPUs in our new M4 instance. We've recently announced an instance called X1 that will have up to 100 vCPUs. When we use that term vCPUs, by the way, we're really talking about hyperthreads that we're exposing to the customers. So if you're interested in physical core counts for these largest instance types, simply take that number and divide by half. So 100 vCPU X1 would be a quad socket E7 based server in which we're offering you 50 physical cores, 100 hyperthreads, 100 vCPUs. Our website lists the details of all these. I'm just going to show a few here. If you think about an instance type like a C4, that is going to be based on E5 processors. This one, we actually use a custom processor developed in conjunction, of course, with Intel, the E5-2666. You won't find that in the specifications on the Intel site. It's specific to Amazon. We've worked very closely with them to develop an instance type, an instance family, the C666, that has performance and the capabilities that we need in the cloud environment. And this provides very high performance for our customers. They have access to turbo, and as I said before, AVX2 and other capabilities. All of these instance types, C4, C3, R3, you'll hear these names, come in different sizes. Some people like to think of them as t-shirt sizes, right? So here, for example, there are 5, ranging from the C4 large, which is listed as having 2 vCPUs. That really means it's a single physical core. A certain amount of memory. In this case, the storage, there's no attached storage on these particular instance types. It's all elastic block storage, which is a proprietary network-attached SSD-based storage, quite high performance. And then they range up to these largest ones, in this case, the C4 8X large, which has 36 vCPUs, 18 physical cores. Our newest family, M4, similar, but it has more memory. So this is also a Haswell-based instance type. You can see that it has more memory, about double the memory of the C4s, slightly lower clock speed, so we have a compromise there between clock speed and the amount of RAM in this M4. It's more of a general purpose instance type. And we have other instance types like R3 that have substantially more memory. We've announced recently our X1, which will be coming out in 2016, and that will have up to 2 terabytes of memory in the largest size of this X1 instance type. So that's a very high performance instance type, high memory. It's primarily intended for applications like SAP HANA and other in-memory types of applications in the IT space, but we also think that the HPC community, in fact, we have a lot of feedback from the HPC community that this will be a very important part of a typical HPC cluster, whether it's a head node or whether it is an actual worker node doing a memory-intensive computation. Let's talk a little bit about networks. Amazon Web Services is operating at such scale now that we really design and build everything on the network layer. Our networks are nothing like you've seen before. There have been presentations at some of our events that you can find online, our reInvent conference, for example, that describe this in more detail than I will try to today. But it is a proprietary 10 gigabit Ethernet network built for extremely high scale, for high consistency of performance, right? And it scales actually quite well for many of the traditional HPC codes. I mentioned CFD before. It does not have the latency characteristics, the low latency characteristics of solutions like InfiniBand and others. So scalability for many of these codes in CFD and in MPI types of applications can be limited. But we're finding in our enterprise customers and research customers that are doing benchmarks and actually testing CFD, weather simulations, and other types of applications, the scalability is actually quite good of these instance types up to some scale. And that scale is going to depend entirely on the application and the models that you're attempting to simulate. The major benefit of running in AWS is you can now run tremendous numbers of these simulations in parallel. So you think about a parameter study in CFD where you want to run 1,000 models in parallel with different parameters. You can do that on the cloud and scale extremely wide. But even within each one of those simulations, you can scale surprisingly large on a typical HPC job, even if it's tightly coupled MPI. But you really need to test. So please, and again, the credits that we will offer today, if you want to do some of that testing, we have a tutorial that I'll talk about in a moment where you can run some CFD tests for yourself and see how it scales. I'll talk a little bit about the consumption models for cloud. There are 3 basic ways that you can consume AWS EC2, Elastic Compute Cloud instances, 3 pricing models, if you will. The first of these is on-demand computing, pay by the hour. Some people call this coin-op computing. You just keep feeding the meter, and as long as you keep feeding the meter, you can continue to use that instance on a pay-per-hour basis. No commitments. As long as you want to use it, you pay for it. When you're done, shut it off, stop playing. It's simple. It's easy to get started, no commitments. Great way to get going. If you want to run over a long term or at very high scale, you should think about some alternative methods of paying for services. One of these, the long-term commitment, whether it's 1 year or 3 year, would be reserved instances. So in that case, for example, you want to run a database or the head node of your cluster, or maybe you have some base level of workload that you need to run every day. You can purchase a reservation. That will give you a significant cost benefit, and you'll also get that reservation, that capacity reservation as well. The third model is the one that's most interesting for HPC, and in fact all of the examples I cited earlier, whether it's Disney doing animations, whether it's HGST doing disk drive simulations, Honda has spoken about how they use material science simulations on AWS, many customers, Novartis and others, they use spot instances. If you haven't heard of spot instances, these are incredibly powerful. It's a bidding mechanism, it's an auction mechanism to get access to our excess capacity. Now, our excess capacity at any given time in these different instance types, in the different regions around the world, is very large. And so we have thousands of customers at any given time that are running spot instances for high-scale workloads. So it's a bidding mechanism. The trade-off with spot instances, because it's a bidding mechanism, if you are outbid during the course of your job for one server or perhaps multiple servers, then your server can be terminated with 2 minutes of notification. That sounds terrible if you're running a database, but it's just fine if you're running large-scale Monte Carlo simulations or, as I said, parameter sweeps, and you can simply restart the job or shift it to another instance type. Or run Bitcoins.
I don't imagine that's cost-effective.
It is not cost-effective. No. So in reality, what most of our enterprise customers do, and I mentioned use cases before, is they'll run a combination of these models. Reserved instances, they'll run, as I said, for things like licensed servers and cluster head nodes perhaps, databases and the like, because those are long-term jobs, right? They want that price advantage and the long-term reservation. If they have workloads that are not fault tolerant, that the cost of actually losing that instance might be quite high, because of the restart need, then they'll run those on demand. But the difference in price between running on demand hourly on AWS and running on spot can be as much as 90% off on spot, a 10x reduction in price by running on spot. So customers that are running on demand and scaling up and scaling down, they pretty quickly figure out how to put automation in place, how to use some of the capabilities that we provide to help manage that bidding across different instance types. And what we see with customers again and again is that once they get to a certain scale, they begin to scale up dramatically on AWS, we see their use of spot scaling up quite dramatically and their use of on-demand tapering off because they learn how to manage interruption. I want to talk a little bit about spot because it's so important for HPC, and it's how I'd really like you, if you use these credits and this tutorial that we'll provide, to take advantage of spot so that you can run at high scale and really pay very little for your compute. So spot is basically an auction model, right? You're going to bid a price, the maximum that you're willing to pay for a given hour of compute for a given instance type, right? As long as the supply of that instance type is greater than the demand, there's actually more supply than there are bidders, that price will stay at a very low level, very cheap, right? And that'll be less than you bid, and that's all you will pay. You won't pay your bid price, you'll pay that floor price. It's only when there's more demand for that particular instance type in a particular pool of capacity that the price will start to come up, because now you have a bidding situation between these different customers. And as soon as that bid price or that market price goes above your bid price, you'll get a notification, 2 minutes, and your instance will be shut down, right? So it's fairly simple rules as to how we operate it. To use it effectively, there's some things that you need to keep in mind. You need to think about building stateless applications, right? So applications where the data is not, necessarily resident on that instance and you have to checkpoint all the time or save state somewhere, right? Fault tolerance is a big deal. So again, if you can figure out for your applications how to automate this so that when a given worker node goes down, you can just spin it up elsewhere, restart that job. There are certain application patterns out there like Hadoop. They're just kind of inherently fault tolerant and stateless. They work extremely well on Spot. We have super high volume customers running Spot Hadoop jobs on a daily basis. Monte Carlo simulations are another one that are great for this. Fault tolerance is almost inherent in those. Diversification is also important. So if you can diversify across different instance types, use multiple availability zones on AWS, even multiple geographical regions, you can have a much higher success rate of running very high-scale jobs on AWS. And then loosely coupled. So think of Spot as being the world's largest compute grid, right? So you can go out and just scavenge cores on Spot for your very large runs. As I mentioned before, instance flexibility is important as well. So if you can run on a C4, on a C3, on an M4, set up an environment on Spot where you're actually diversifying across different instance types and managing your deployments as the prices change. That's how you can get extremely high scale, and there are third-party products that can help you do that. Spot is different capacity pools, as I said, so the prices for C3, for example, of a certain size and a certain availability zone may be different than that same instance type in another availability zone. So customers that are taking advantage of this will use automation or use capabilities that we provide in order to examine the price and automatically shut down servers in one region or one pool and start them up in another one based on the observed prices. Customers that do that, as I said, they can operate at extremely high scale with high reliability day after day running many, many thousands of cores. Lastly, I want to mention again that the price that you bid on Spot is not the price you're going to pay. There's always a market price, and if that current supply of that particular instance type in that pool is higher than the demand, that price is extremely low. Often 10% of the on-demand price, of the typical full price on-demand pricing. Last note about Spot, we've been rolling out a lot of new capabilities around Spot. One of those is called the Spot Bid Advisor. So now you can go to our website, and rather than just making a guess about where you might get the least likelihood of termination and the most efficient pricing, you can go to the Spot Bid Advisor now that's on aws.amazon.com in your console, and you can find out, for example, a C3 of a certain size or a C4, you can filter it down what types of instances are appropriate for your workload, and you can find out what the likelihood of termination is and the observed cost savings over on demand that customers are getting on that instance type. It's a very, very useful tool if you're using Spot at scale. So to kind of end this, we have a tutorial that we've stood up. If you would like to get started with AWS, you can do it at no cost. You create an account, we'll give you the credits, $100 worth of compute credits, which actually, if you could play the spot market intelligently, on a per CPU basis, you could actually get as many as 10,000 core hours, vCPU hours on Spot using these $100 of credits. So you can run lots of different simulations, try things out over the course of a few days. And in fact, with this tutorial, you can stand up a large Spot cluster or a small one that you want to run many jobs on very quickly in a matter of minutes. I'm not going to go through that whole tutorial here in the few minutes we have left, but we have cards that we can give you that have the web address so that you don't lose it, or you can take a picture of this link. Do not tweet it. The reason I say do not tweet it is because there's a link to a registration page, and that registration page will only accept the first 250 requests for those credits. So if you want them, don't tweet this out, certainly for a few days, and then we'll let anyone who's still in the pool go get them. But this is a very useful tutorial. It's highly automated. So once you sign up with your AWS credentials, you apply for the credits, you put them in the account, and then you walk through this tutorial that shouldn't take you more than 20 or 30 minutes to get through the whole thing. you can run some OpenFOAM simulations on multiple instances, right? So I think it's up to 32 physical cores, 64 hyperthreads of OpenFOAM for these jobs. And you can modify that, the scripts and the tutorials. This is based on a tool that we provide called CFN Cluster under the hood. If you want to dive deeper into how to deploy onto AWS, go to our aws.amazon.com/HPC page and look at CFN Cluster. It is a great tutorial. It's a great set of cloud formation templates that will help you get started and understand more completely how to run simulations on AWS. This is the one I didn't want you to tweet. So the SC15/giveaway. Again, we've got cards that you can take on the way out that have this information on them, $100 of credits that, again, on spot will run quite a bit of compute for you. Wolfgang just tweeted it. I did not.
Oh, you're very careful. Thank you.
No worries. Another great resource is our AWS architectures page. Lots of use cases are described there outside of HPC. There is at least one HPC architecture example in here, but this is a great page to understand how to create scalable websites, how to stand up a DR type of environment using a VPC, right? How to do big data and Hadoop analytics. It's very useful for a quick introduction to how to stand up these different architectures on AWS. Resources again, /HPC page, great place to go. There's a white paper there that you can download about HPC on the cloud, some of the use cases I described before, as well as links to that CFN cluster page that I mentioned earlier.